Great. It's a great pleasure to welcome Daniel Tubbenhauer, who will tell us about tilting modules and poles.
Thank you very much, Ben, for the introduction. Exactly, I'm going to talk about poles, and also for the invitation, of course. It's always a pleasure to come to Eugene, this time even saving the planet, not boarding an airplane. Everything I'm going to talk about is joint work with Paul, who should be in the audience somewhere. And, well, the whole story started a little bit like I wanted to understand those categories of tilting modules, which I'm going to recall in a few slides. And, well, I did so with very early work with Henning Andersen, the quantum group case. And I just thought, so characteristic P, quantum group heterodynamitity, it shouldn't be too different. So let's try characteristic P. Just as a spoiler, I was very naive. So characteristic P is just much more complicated and also much more interesting compared to the quantum group heterodynamitity. And I will make this pretty precise, staying with SL2 for most of the time. So if you never heard about representation theory and characteristic P, then you're exactly in my position. I have no idea about it. So let's just start from scratch with SL2 itself. And my first slide. And I thought, at least on the first slide, right, this conference is called QUACS, so quantum groups, categorification, and circle bimodules. I'm going to talk about neither of them. So no categorification, no circle bimodules, also no quantum groups. But I should at least start with a little bit of quantum to make sure, right? I started this whole project thinking quantum group heterodynamitity and characteristic P. It's basically the same. It's not. And here's the reason why. Morally speaking, the reason why. This nice folk theorem, due to, well, it's a folk theorem, but it's sometimes contributed to Lucas. It's very old, of course, and it's just a very naive question. So I have my, let's say, quantum binomial A over B, and I'm in quantum characteristic P. That just means the smallest number that my quantum number vanishes, right? If Q equals 1, this is just the usual characteristic. So how on earth can I compute this funny binomial? Well, it's very nice, actually. You just express your two numbers A and B. Here's A. Oops, here's B. Maybe I should A and B, and you just express them periodically. And well, you could split the binomial, the quantum binomial, into a binomial just carrying about the zeroth digit in your periodic expansion, and the binomial keeping track of the rest. Okay, and by the way, this is no typo. This is a quantum binomial. This is a regular binomial. We'll see it in a second live in action. And kind of the whole philosophy I want to sell today is only the order of vanishing of this binomial matters in characteristic P and in the quantum group case and for tilting modules and simples and everything in the representation theory of category of SL2. And I kind of claim, so I wrote SL2 here. And I kind of claim that this immediately gives all those 4 cases, which I will zoom in on the first one and on the last one, and I'm kind of want to implicitly explain the other ones as well, but I'm not going to do that. So I kind of claim that this is enough. This very old theorem is enough to completely nail down the representation theory of SL2. Okay. So before I zoom in on that, let's try to understand this theorem really on the nose. So first of all, in my characteristic P case, so Q is 1, and my field is a field of characteristic P. Look at this theorem, right? So you get a binomial, you split it into 2 binomials. You can't do anything more here. This is already kind of minimal, but you can further split this one along its digits. So in characteristic P, and that's why it's called Lucas theorem. He was really interested in well, of course, he was not interested in the quantum case, just in the characteristic P case. You can compute your binomial as just the product of the binomials of the digits of your periodic expansion. Right? So expand it periodically and just take the product of the binomials. Note, however, in the quantum case, you're kind of stuck, right? You can't express this any further. This is kind of the real difference between characteristic P and the quantum group. So let's do a really on-the-nose example, really honest example. So I take b equals 1, completely forget it. So I take this b is 1. I don't want to care. And I take this 1331, which happens to be 11 cubed because I've done my homework and of course chosen this example very carefully. And okay, right? Generic case, quantum group case, this mixed case, and the main beast, the characteristic P. Okay, so generically, okay, quantum characteristic is 0. I have nothing to do. It doesn't vanish, right? Shouldn't surprise you. Binomials don't die in characteristic 0, right? Quantum group case. So what do? Well, you express it 11 radically, but you only care about the 0th digit, and this guy will vanish of order 1 because you get really 11 squared here, which is not 0 if I were to see. The mixed case is kind of the mixture. So let me zoom in on this case. In characteristic P, you just express your number periodically, and you count all 0 digits that you see, and this actually vanishes of order 3. And you can already really see the difference between all of those cases. So here in the generic case, which I will call generation 0, this guy will never vanish. Okay. No matter how big my numbers get in this quantum group case, I can never have a pole or a vanishing of order more than 1. Actually, that gets completely periodic. It might flip over and flip over and flip over and flip over again. This is generation 1. This is kind of a mixture, and this gets as bad as you want, right? If A gets big, it could have 504 0 digits, and this might vanish to order 504. Right? And all due to this Knight theorem due to Luca. And I claim that's exactly enough, or that's completely enough to understand the representation theory of SL2. Okay, so I will zoom in now to characteristic P, but kind of you should think of the quantum group case is really a generation 1, and the main beast characteristic P is infinitely more complicated than the quantum group. I started completely naively. I believed that they are almost the same, but no. It's infinitely more complicated in a really good way. And the mixed case, which I'm not going to address anyway, is kind of infinity minus 1, if you want. It's still very complicated, but not as complicated as the main beast. It's just a pain to write down, so I don't know. Okay, such that we are all on the same page, I want to recall the Weil modules, and they really go back to Weil. They're very easy for SL2, right? They're just, well, you have the 0-dimensional one, you have the one-dimensional one, you have the 2-dimensional one, the 3-dimensional one, and so on. And they arrange themselves so nicely in this Pascal triangle. And the action is, I mean, this is the symmetric powers, right? So the action matrix is of my SL2 matrix here, ABCD, is just the column expansion of the corresponding two polynomials here in my variables x and y. Okay, and you will see something funny here. So the real interesting number will be this v, and not the highest weight. The highest weight is v minus 1, but the interesting number is v. I don't want to call it the dimension because the generalization is that I should take my highest weight plus rho. In this case, it happens to be the dimension, but in general, it's the highest weight plus rho. It's the important number. In this case, just v instead of v minus 1. So for the 0 module, for the trivial module, the number 1 is the important one, not the number 0, and so on. You will see in a second why. So the example, this delta 0 minus 1, you just expand. So this matrix acts by expanding the columns of the matrix according to this rule. And of course, you see binomials. I mean, this is binomial coefficients, right? And the funny thing that then happens is you just use this Lucas theorem. And I don't really tell you why, but really you should look at the action of this funny matrix, which isn't an SL2 matrix at all, but it happens to be the important matrix. It's sometimes called the total matrix. And you just check what happens. And okay, you get a little bunch of numbers, all those binomials. And of course, there are no zeros. So this guy actually is a simple modular characteristic. So all of n characters is 0. All of these are the simple modules. They're symmetric powers in characteristic 0. In characteristic 5, well, you can already see it, right? 15, 20, 15. All of these die, and you have found a submodule, actually. So in characteristic 5, this guy turns out to be not simple. And of course, this generalizes in the following way. It's pretty nice. A well-known theorem, I think, is due to Janssen. This guy is simple if and only if the binomial doesn't vanish for all w smaller than v. And if you can use, let's say, your characteristic p, then by Lucas' theorem, this almost never happens. Namely, only if v is a prime power. Right? In characteristic 0, of course, this will always be true, so they're always simple. Okay, so these are the Weyl modules. And below here, you see one of those boxes will appear several times. That's kind of the general statement here. I'm giving you an overview of SL2, but there's a lot of things that actually generalize. You don't need to read all of this. For instance, well, okay, there's a Weyl module, there's a dual Weyl module. I won't be too careful to distinguish them. What is the point about Weyl modules in general? Well, they are defined integrally. They're always defined integrally. They don't depend on the characteristic. They depend on the characteristic or your root of unity or whatever, only in the sense that they will split further into smaller simples. But as a module, they are always defined integrally. They always exist, and they have the classical characters given by Weyl's character formula. That's why they are called Weyl modules. And you actually, there is really, in Janssen's thesis, there's actually a criterion in general for your favorite Lie group, semi-simple Lie group, whatever, type B 405. You will find some root theoretical criterion which has those binomials as well to check whether this is simple. This is just really a tiny case of a more general story. Anyway, we don't need to remember that. You only need to remember this statement. Whether it's simple only depends by Lucas' theorem. By Lucas' theorem is if and only if it's prime power, and it really depends on the vanishing of those coefficients. Okay, I have a link here. I don't want to click on it. I want you to click on it, so you can click on it later. The slides are online, I hope, on the Quacks webpage or also on my webpage if you want to find it. Because now you can do actually better than this. You can play this theorem to actually pick out exactly the simples. But I want to do the opposite. I want to go to the tilting modules and show you the game for the tilting modules, which is also very nice. Okay, so up to this point, I had those Weyl modules, and they're very nice. What makes them so nice is that they're defined integrally, right? Exist in any characteristic, are independent basically of the characteristic. And I want to kind of find the simples. Well, in the branch of categorification, I grew up actually in abelian categories, not so nice, and an additive category is very nice. So instead of looking at the simples, I should actually look at some intercomposable modules. And these tilting modules, in particular, the way I define them here, I will comment on that in a second. You should think of them, if you like finite dimensional algebras, as kind of the equivalent of projective indecomposables, right? You have simples, you have projective indecomposables, and it's not quite clear which one should play the role of the elements in your story. These are simples when you like abelian categories, or projective indecomposables if you like additive categories, and these are more like the additive version. In particular, here's my definition. Well, it's maybe not the definition you have seen in general. Here's again the general box. You can see it here. So the general definition. I just define them as to be the indecomposable tilting modules, or the tilting modules in general, then are just the indecomposable summands of the tensor product, and this is just the vector representation, right? So delta 1 is just the vector representation itself, the two-dimensional representation. And that's what I want to call a tilting module. Tilting modules are the indecomposable summands of something very nice, like the projective indecomposables are indecomposable summands of something very nice. Okay, and it turns out that they behave kind of in the opposite way than the simples. For instance, they are again parametrized by dominant integral rates. They have this nice reciprocity. They really behave in the opposite way as the simples. The delta factor will appear in T as often as whatever the simple will appear in the corresponding nabla or delta. So as I said, don't worry about deltas or nablas. They're dual, so Weyl modules and dual Weyl modules, they're not really different. I will treat them equally. in particular because I will go to characteristic 0 in a second. And then they are just the same. In general, they're different. Anyway. And what makes it so interesting, so you have three natural bases of the Grothendieck group, of those representation categories, and they are all unitriangular with respect to each other. You have the basis of simples, you have the basis of Weyl modules or dual Weyl modules, and you have the basis of tilting modules. Each one of them, it's really like with simples and projectors, and let's say you have a nice finite dimensional algebra where you have some standard modules sitting in between. It's really exactly the same story. And I mean, this looks exactly like the slide here, and it's really almost the same. And what I want to describe is the scattering tilt by generator interrelations. That's what I'm up for. Because I think, okay, these are my projective indecomposables for finite dimensional algebras. So why not give it a shot to describe it by generators interrelations? And you will see in a second, actually, why this is an interesting question if you're not already convinced. Let me just zoom into my strategy before I continue. So this tilting modules actually, they want to be characteristic 0 things, right? So in particular, they have this nice Hom formula. You don't have to look at it too much. I will just click on the link in a second, because they satisfy a version of source lemma. You can determine the dimension of the Hom spaces between two tilting modules by just looking at their nabla factors or the delta factors. And why do I call this source lemma? Well, so here's my philosophy how I want to think about those tilting modules. They are the indecomposable summands of the tensor product. And all you know in characteristic 0, well, the indecomposable summands of the tensor product is semi-simple, will be the simples, they will be those Weyl modules. Okay, so in characteristic 0, there will be zillions of those idempotents splitting off those Weyl modules. Very nice. In characteristic P, you will realize that those idempotents are not really idempotents anymore because they're not well defined because they have poles in their expressions. Said otherwise, if you work over Z and you just multiply with the corresponding eigenvalue of your idempotent, you get a pseudo idempotent, and this pseudo idempotent you can either rescale it if you're in characteristic 0 because everything's nice and you can just divide by your numbers, or it will die. It will be nilpotent because you say something divisible by p term. But still, you have this nice Hom formula. And I kind of want to play this following game. I just assume that I know my character of my tilting module in the Grothendieck group. I know that it will look something like this. There will be a base change matrix between my tilting module and my delta modules. My delta modules are the integral modules. They are nice. They're in characteristic 0. They are in characteristic 0. They are simple and so on. They are well known, symmetric powers. Very nice. And I just pretend, I define tilting module T bar, and I just pretend it's in characteristic 0. So I just take the direct sum of the corresponding modules turning up. And this really is a philosophy I want to do here. I never want to go to characteristic P, or at least not as long as I can, right? Because characteristic P is really complicated. Okay? And I'm not doing anything complicated. So just don't do it. Just pretend you're in characteristic 0. And then it actually turns out, so that's why I call the Schwarz lemma, that the dimension, for example, the dimension of the one I'm interested in, the tilting module in characteristic P, is actually the dimension of my funny tilting module in characteristic 0, which of course is just the direct sum of simple modules. So this is just by Schur's lemma, you can just, well, you get 1 here and those guys squared. So this is really Schur's lemma. And if you look back on this formula, that's exactly the formula, just that you have to be careful to distinguish delta and number 1. That's the only difference. Right. So I call this Weyl clustering. So what's going on? Okay, I have my Weyl factors. They sit in my tensor product no matter what. You can't get rid of them. They're integral. They're always there. Okay. In characteristic 0, they split off. They will be the simples. In characteristic P, they cluster together and form those funny tilting modules. So each tilting module is actually built out like this one, built out of those nabla factors, and they just split off in characteristic P because you have those idempotents which have poles, but they don't in characteristic, sorry, the other way. They split off in characteristic 0, but they don't in characteristic P. However, those tilting modules are built such that my strategy will work. You will see, I will do a lot of calculations, which are completely bonkers. I will divide by 0 all the time, and I still get the correct result. You won't see it. It will be fun. I can just pretend I'm in characteristic 0 and I will still get the correct results, right? So those two end spaces are completely different. This is just a matrix algebra, and this is the one I want to compute. But I still want to do computations here, and then play some trick to pull everything over. Right? At the very end, I want to pull everything over, and I get a generator and relation presentation of this end space here for any lambda, for any home space, you know. This kind of the
What's MDG in that sum?
Um,
In the picture that pops up. What's ND? There's a direct sum over NDG.
I will explain it in a second. I will explain it in a second. Okay, so what I haven't explained, so what Ben was basically asking is how to determine those guys here, because I want to have this module. And this is NDG, I will explain it now. Okay, but this is the strategy. Never go to characteristic P, that's way too hard. Just stay in characteristic 0 as long as you can, because tilting modules are built such that they work in characteristic 0. Okay, and because they are built out of those nice modules, those integral modules, So here comes the question Ben was asking. Of course, there should be a way to determine, just using vanishing of binomials, to determine the Weil factors that turn up, because those are really the poles that you see in those idempotents. I will come back to this in a second. And that's what I will call NEG in a second. So for instance, I want to compute the number of Weil factors of my TV, and I only need to take the maximum vanishing order of my quantum binomials. Right? So here's an explicit example. Probably the biggest number, no, this huge is the biggest number I ever used in a talk, but anyway, so what do? You take the number V, whatever it is. You shouldn't look at this expression, it's horrible anyway. You should look at this expression, the p-adic extension. Right? So you see 1, 2, 3, 4 non-zero digits, so we will have 2 to the 4 Weil factors turning up. You can check that the maximal vanishing actually appears for this guy, and you can check that this guy is divisible by order 4. Okay? So vanishing the poles, the zeros, or the divisibility by p of the binomials.
That looks like 5 right there.
And no, this is not 0.
Oh, sorry.
4. Yeah, sorry, I don't have a good expression for it, but this is non-zero. Yeah, this one. Okay, good. And this NEG is a negative digit game. I can actually use exactly the same strategy to figure out what kind of Weil factors I have. So I'm using here my strategy, and just write it down. And the Weil factors that appear are exactly inverting the non-zero digits. For instance, this one will appear. And let me make this completely precise. So here, this is exactly the same example, right? 200 whatever. And you would just take those digits and you invert one at a time, and just have 16 of them, and those would be the corresponding Weil factors. Of course, you don't want to think of this in terms of those numbers. You want to think of them, in terms of those inverted scalars. Okay, so very easy. And so I can write down the character in this case very easily by just periodically expanding everything and invert scalars. A comment for the experts: if you think now of the quantum group, you would play the same game. It's exactly the same game, but you only care for the last digit. In particular, your Weil factors, in this case, of course, your Weil factors, your tilting modules can have as many Weil factors as you want, right? 2 to the k for some k. In the quantum group case, k is at most 1. So you either are simple or you have 2 Weil factors, right? Why? Because you would only care about the 0 digit because of the vanishing of the quantum binomial by Lucas theorem. Okay, it's almost time for a break. Perfect. So this is my strategical interlude, my slide for the break. So here we are. We start knowing nothing. I want to define. You can already see the links. I want to define a category given by generators and relations, which in the end will turn out to be integrally equivalent to some category generated by those integral modules, by those Weil modules. And I want to find certain bases of this. I will zoom in a second, of course. And the main players will be the tilting basis and the standard basis. And I want to compute the base change matrix, and everything in green is still not doing anything in characteristic P. And then I have to go to characteristic P and I have to make sure that my poles actually don't exist. Right? I got rid of all the poles. And I don't know how to, well, we will see. I will see in a second. And I think in the end, what drops out will be the quiver. And I will explain the quiver as well as the way to actually get the quiver. And I think that's a good point for a break.
All right, we'll break until 30 and ask questions.
Yeah, I guess my question is, looking at this strategy page, so it seems like part of this strategy is already knowing what the character of the tilting module is.
You're a little bit ahead of everyone here, or at least ahead of me. I have my thing. I need to know what the tilting character is. That's exactly correct.
Right.
That's what I want to get rid of. I think there should be a purely diagrammatic way, we'll see it in a second, to not having to do this, but at the moment I have to rely on knowing what the tilting characters are. And that's of course a huge problem, because from SL3 onwards, I just don't know what they are, right? But I'm hoping to kind of have, in the future, I would have a strategy which avoids this, okay? Yeah, so here, the only thing that is known from SL3 onwards are actually the tilting characters for generation 1, which is a quantum group. And for generation 2, there are some conjectures, but that's basically it. So Ben is completely correct. My strategy fails in this red box for now. So if anyone knows a nice answer, you will see it in a second, how to get rid of my assumption that I know the tilting characters, I would be happy to hear it.
And in particular, right, like, I mean, the rank of this matrix reduced mod P, I mean, this is, you know, right, this is like, you know, goes back to Janssen. And like,
that's correct.
The whole problem for people is they couldn't calculate the rank of that matrix.
Right, it's hard, I know. I mean, there's a reason why characteristic P is so hard.
But so you're saying you're hoping there's a diagrammatic way of doing it. Is
Correct,
that going to hide again what the characters are? Right. I mean, this is one of these things that I feel like is kind of one of these iron laws,
So,
right? Where if you have a multiplicity that you need to like do Kazhdan-Lustig to compute, then like either you can get a nice description of things that hides what the multiplicities are and you don't know what the dimensions of the simples are, or if you try to do some formulation where you know what the dimensions of the simples are, then you get a huge mess because like it's hard.
Right, but no, I mean, the point is, in everything I'm going to do, I never use anything like the Frobenius twist, for instance. So there might be a different strategy somewhere, and there might be a completely diagrammatic argument to just avoid knowing the tilting characters. But for now, I just don't know any. That's just how it is. And that's why I call this my original sin. This is where everything kind of depends on something I don't want it to depend on.
Yeah, life is tough sometimes.
I had sorry, it's a little noisy in the background here. This is Monica. I had a question from one of your very early slides when you had the examples with P equals 11. And you had written this, you know, Q car equals 10. And we weren't sure if it was a typo or what it meant.
Okay. Somewhere here.
Okay, so then there, this slide. Yeah, on the third line, when you have if K is F11 bar and Q is 2. And then
2 in characteristic 11 is a 10th root of unity. So the quantum characteristic is actually 10.
Okay, so some people had suggested that. Okay.
If I have done my homework correct, of course.
Any more questions before we start again? Then let's start again.
Okay, so thank you very much for for the questions of us. Okay, so let me go to this category web. I'm pretty sure most of you know it, but let's just do it. So the historically wrong name for this category is temporally leap category. The historically correct name for this category is Rubber-Teller-Weil category. In order to not confuse anyone, I decided to call it web, because of course there is a more general approach using webs, which we have seen in actually the first talk today. So anyway, it's pretty simple in this case, and it's just a monoidal category, Z linear, and it's generated by just one stupid object, and there are just two morphisms, which I call cap and cap, and they're of course co-evaluation and evaluation, and all of you have seen those relations before. In particular, up to, there might be something strange going on in characteristic 2. This looks very nice. Okay. Okay, so this is my category. I want just to do the temporally leap category, or how I would call it, web. Okay, and if you have never seen this category before, here are some examples. So this crossing, the Kaufman bracket formula is actually really already in this paper, right? And the paper actually, you will see it again. So the correct name of this category should be actually Rubber-Teller-Weil. Anyway, so if you had draw crossings, then here are some examples. I could stack this on top of this one on top of this one, and I would get a picture like this, and I would get a -2 here by just removing that circle right now. And of course, this has generalized quite a bit. And if I don't want to do characteristic P, but let's say it's a quantum group, then I think what I'm going to say generalizes to at least type A. Because in type A, I would know, coming back to Ben's question, in type A, I actually know the tilting characters for the quantum group, which are given by certain custom-string polynomials. Okay, so temporally leap or web or whatever you want to call it. And now I want to find those bases. And I claim this is all the same. They all work in the same way. I want to find it. I mean, it's an integral category. I should find an integral basis. And I want to find a standard basis, and I want to find a tilting basis. Before I do, well, let's do it. Let's just do it. And this also goes back to Rubber-Teller-Weil, but I actually learned it from a paper of Ben, in which he does the general SLN case. It's a very general strategy. It works as follows. Right? We're doing characteristic P without doing characteristic P. We'll see it in a second. So my completely generic SL2 fusion rules, all of you have seen this before, like multiplication by 1. And this corresponds to 2 directions in my SL2 weight lattice, right? SL2 weight lattice is a bit boring, it's just a line, but I have 2 directions. And I have 2 natural maps I associate to each direction. And for each, formally speaking, for each path in my dominant Weil chamber, I will zoom in on an example in a second, I would define a certain web, a certain diagram inductively by, well, whenever I see this direction, I just put a strand next to it. Whenever I see this direction, I cap off the last strand I see. And this inductively builds me an element which I then stick together to get the usual crossingless matching basis, as explained a long time ago by those guys. And by Ben in more generality. And this is how it works, really, in this case. So what is a dominant Weil chamber for SL2? It's just a positive natural numbers. And here would be a legal path, right? I go plus, plus, minus, plus. And I stay always in my positive Weil chamber. Or I go minus, plus. This is a non-example, right? I leave my positive Weil chamber. So I only take those guys. And let's say, then what do you do in order to calculate this basis? You just list all of them. So I've listed all of length, 4 boundary points. You can write down the corresponding, using exactly the strategy, write down the corresponding basis elements, like, okay, plus the 1, 1, 1, 1, 1, so the plus, 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 just 4 strands. What is this one, for instance? This one, the 2, well, it's here, and you put a strand, and now you see a minus, you cap it off, you put a strand, you put a strand. Let's do this one. You put a strand, you put a strand, you put a strand, you cap it off. Right? This one, you put a strand, you put a strand, you cap off the strand, you cap off the strand. This is how you build the bases. And then you stick them together using the usual strategy that this is kind of the lower part of the diagram. These are all basis elements, and they should look very familiar. These are the crossing and matching bases of the Tubbenhauer algebra, just explained in a nice way, right? Just explained in a way where you think, oh yeah, I can generalize to my favorite type B100 and B504 as long as I have some reasonable web calculus, which is still missing, by the way. So Ben explains how to generalize this to SLA. Okay. Okay, so this is a nice basis, integral basis. You never see any coefficients turning up, right? I start with identity, I put a strand or I cap it off. Put a strand, cap it off, put a strand, cap it off. You never see that. You never see any funny coefficients. Okay, and now I want to play the same game. It's exactly the same game. So what is happening here? Well, kind of, you can see it here, kind of, wherever you go, it tells you the highest weight space your morphism will factor through. Okay, I'm going through a certain weight space, but maybe I don't want to just randomly go through this weight space, but I rather want to pick out my Weil factor, my indecomposable, my simple Weil factor. Remember, we are still in characteristic 0. Right? So what I do, well, it's exactly the same rule, but every time I use a projector. Okay, this projector, if you've never seen it, doesn't matter. There's a projector to the highest summand in the corresponding weight space. It's called the Jones-Venzel projector. And you just plot it in every time you do this. And note that the only thing you need to know about those projectors, they have funny coefficients turning up. In particular, they have coefficients that will be almost always divisible by p. So this basis is really a basis, as it should, as you see in a second, is really a basis that only makes sense in characteristic 0. But anyway, the diagrams look exactly the same. You just stick it in each step, you stick in a projector. That's the only difference. Okay, so integral basis defined using the fusion rule. This funny basis having the projectors defined using the fusion rule. And you would guess, okay, maybe we can play the same game. Again, I need to know the tilting characters at the moment to play this game. But anyway, you can write down this tilting projector. This projects to my T bar. And you just stick it in exactly the same way, completely inductively. So let me show you actually how those guys look like. So here, this is one of those projectors. So what is going on here? So I don't worry about these coefficients too much. You can write them down explicitly. So each one of those funny boxes here is a Jones-Venzel projector. So you have a lot of them, and all of them have poles. Almost all of them have poles, so it doesn't really make sense to write this down in characteristic P. And then I take a certain sum of them. Okay, why do I want to do that? Let us think about it. Okay, I know that this is my tilting, so this is T bar for the corresponding VE. And, well, remember my negative digit game. So this one will factor. So this here you see the one of the Weil factors in this expression. Here you see the top Weil factor. Here's another Weil factor. Here's another Weil factor. So I just sum, right? In characteristic 0, this splits off. This idempotent splits off one of the Weil factors. This idempotent splits off the other Weil factor, and so on and so on. They don't make sense in characteristic 0, in characteristic P, but their sum is well defined in characteristic P, which is a lot of fun. So each term separately contains zillions of poles, and here you actually see more poles, right? The zeroth digit is already a 0 here, which means it's divisible by p. You have poles, 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 poles all over the place. You take a sum, and this guy will be well defined. And in order to show that this is well defined, I need to know the tilting characters. But I think you should be able to show that they are, coming back to Ben's question, that they are well defined, not knowing the tilting characters, which is a very hard exercise. I don't know how to do it in resource Jones-Venzel projectors in diagrammatic calculus. But anyway, the strategy is still the same. I'm in characteristic 0. I sum up my projectors, which are totally fine in characteristic 0, which are horrible, not well defined in characteristic P. I get something well defined and I'm happy. And I claim that's correct. I can still stay in characteristic 0, and all of them are basically orthogonal idempotents, and I can continue my calculations. Okay. All right. So this is how those projectors are built. Just notice there's almost no difference. They're all built using SL2, using fusion roots, using something semi-simple, and just stick in the projector, which makes this not defined in characteristic P, and this one will be well defined in characteristic P. By definition, these will split off the tilting modules, the T bars. This will split off the Weil modules, the deltas, and this is just an integral basis, which kind of goes through the corresponding weight space. Okay, so this is a very general procedure, right? You only need to know those highest rate projectors, and you stick it in according to the fusion rules. And so let me explain why I'm so much interested in those two bases. So this is my I call the basis S, the standard basis. This is the basis I call T, the tilting basis. So why I'm so interested? Okay, they all give bases of the same Hopf spaces, right? That's how they are constructed. I'm still working over in characteristic 0. This one is nice. You will see it in a second. You need it to prove that you're not completely going crazy. But otherwise, it's what it is. Okay, and they're all constructed by this bottleneck principle, which I light letter spaces, light leaf spaces, it's always kind of the same strategy. Cellular bases, whatever you want. But let's focus on those two. So the standard basis, why I'm so interested in this? Well, this is the basis that splits off the delta factors, the simple factors from the tensor product. This is the Artin-Wedderburn basis, right? So all of those basis elements, what kind of relations do they satisfy? They satisfy a completely trivial relation, orthogonal idempotents. So anyone can calculate, that's what you expect, it's a semi-simple category. Anyone can calculate a representative algebra here. It should be something extremely trivial. And this is the one I want. I claim this is the one I want. And if I know the base change matrix between the two, well, and I could express those guys in terms of the easy ones, do some calculations here and pull the relations back. Here it's well defined, here it's crazy, here it's well defined. So I'm starting at A, doing something extremely crazy, divide by 0 all the time in the middle, come back to B, here's B, so A, whoop, doing something crazy, coming back to B, everything is well defined, I claim that's the right result. Okay. This is kind of an Euler type calculation, right? So just shut up and calculate and worry about details later. This is really how it works. This is really how you should work with tilting modules. It's kind of, they are built such that this works. Okay, let me do an extremely explicit example. You don't need to look too much on the details here, but just to show you that my calculations are completely bonkers. They're completely nonsense. Let's get the correct result. Okay, I take my T bar here, just 2 digits. And according to the negative digit game, I would have 2 factors here. Those also 2. You shouldn't express those numbers. You can try it, right? I mean, this is just 11 plus 1. So it should be 12. And this is just 11 minus 1. So it should be 10, I guess. Anyway, just look at the digits. Okay, so I get this basis. I explained how this works. There's 2 basis elements, of course. So I'm just looking for the end space here right now, right? So just end of this tilting model. Okay, it has 2 summons, so it should have been 2-dimensional. It's semi-simple. And these are just orthogonal idempotents. Pretty trivial. And I have this basis B, T, and I wonder what kind of relation does it satisfy? Okay, and I need to compute this base change matrix, which isn't all that hard. It's not trivial, but it isn't all that hard. From T to S, and I claim it looks like this. Note the interesting thing, there's some kappa, whatever. Here is something that is 10 over 11, or the inverse then has 11 over 10. So this is a completely nonsense calculation in characteristic P. Either have a matrix that is not defined, or even not defined, or have a matrix that is certainly not invertible. So either I have a 0 here, or I have even worse, a pole, 10 over 11. I don't care. I just go on. Okay? I just go on. And I express, let's say, this matrix just says that this element is just a scalar multiple of this one. Okay? So this one is an idempotent, so it squares to 1. So what does this element do? Well, it squares to exactly the scalar multiple times the other element, but the scalar multiple turns out to be, that's how it's built, 11 over 10. So this is, by the way, well defined in characteristic P, but it's 0 in characteristic P. So in characteristic 0, it's just a stupid base change, but in characteristic P, now things will die, and you will see, well, if you do your calculation carefully, you will see actually the end space is now in characteristic P, so K is my characteristic P field, isomorphic to the co-modular of the flag variety of SL2, or in less fancy words, it's just Kx mod x squared. Let me stress again that the calculation was completely nonsense, but you get the correct result. So this is how you should work with tilting, right? So the base change matrix doesn't make any sense in characteristic P, but not in characteristic P. So fantastic. That's why I'm interested in this base change matrix. This is the basis I want, because I want to calculate the end spaces or the home spaces between tilting modules. I base change to something that is almost trivial, because it's the Eifel-Wedderburn basis. And I get all my relations, all the relations that I want. Okay, so let me finish to show you, well, okay, then there is this original sin, which makes sure that all poles are not there anymore. So expression A is well defined, expression B is well defined. It doesn't matter what I do in the middle. And then actually I can reduce mod P and I get the proof I want. And let me show it to you because it's extremely beautiful. Maybe you can already guess if you keep on if you keep in mind that I have this game of digits, that it should be something fractal, and you will see it in a second. It is actually really something fractal. Okay, so here's the result. What do I mean by give a generator as a relations presentation? Well, I want to have such a functor f to some projective modules over some Priver algebra, and the Priver is basically generators and relations. So explicitly. And it should identify indecomposable tilting modules with indecomposable projectives. And this is how the Priver looks like. I will zoom in a second. So it has the vertices that corresponding to my V. Of course, there are infinitely many. This is characteristics 3. There will be the corresponding tilting module, and these are its Weil factors. So this tilting module has whatever, those Weil factors. Okay. So the end space here would be 8-dimensional. Right. Here, so everything in red, those are the ones that are semi-simple, so where the T is the nabla when it is simple, and it gets sparser and sparser and sparser. These are only multiples of prime powers by Lucas theorem, right? And otherwise it looks like this. What is the relation is now the question. So this, I think this is pretty nice. You will see in a second why this is completely fractal. So let me zoom in a little bit, right? Characteristic 0, so generation 0, generation 1, generation 2, and then generation infinity. So in generation 1, which I mean by you never go across this line here, right? You see you have just 3 vertices and there's no connection, right? I cut it off here. And of course, that's how it should be. Generation 1, generation 0 is nothing vanishes, everything is well defined. You have something semi-simple. The Priver should be completely boring. It should be just vertices. And if you, of course, continue this periodically, you get the Priver in characteristic 0. That's exactly characteristic 0, right? It's generation 0. This is semi-simple, as I said. The Priver has to be boring, almost by definition. Now, not by definition, but it has to be boring. Anyway, generation 1. Generation 1, I would go to, here's my first, so here, this one shifted by 1. Here's my first vanishing of order 2, no, here it is. And I cut it off here. So this would be generation 1. So you would already see it's not semi-simple. This one is connected to this one, is connected to this one, for example. 2 is connected to 4, is connected to 8, is connected to 10, and so on. So you have connected components, but they're certainly not trivial. And this is this is a 0-digit game, right? Generation 1. So this is the root. If you continue this periodically, you get the quantum group. The quantum group is a complex root of unity. And each connected component is a zigzag algebra. The zigzag algebra, Josh will talk about zigzag algebras in the second or next talk. If you've never seen zigzag algebras, it's pretty easy. Going 2 steps in one direction is 0. And you have the zigzag relation. If you do a loop here or do a loop here, it's just the same. So, well, I can also say in this case it's 0-dimensional and I have a zigzag algebra in each direction I see. I just have not any interesting directions. And here I have a zigzag algebra in my one direction, generation 1, so it's dimension 1. In generation 2, so I would cut it off somewhere here where I see the first crazy guy of a bigger length. Now I have a zigzag algebra in each direction of my potential digits. So they arrange themselves in a grid. And it's really just each column, each row is a zigzag algebra, and you basically have a square compute relation. So the interaction relation between them. But the point is in each dimension, which I would like to think about as being the potential zero digits in your, so the potential poles in your expressions in your periodic expansion. In each direction of a zigzag algebra. And this just continues. There's some scalars and error terms which you probably can scale out. I never bothered about it. But this basically continues, and you should think about this quiver as being kind of an infinite grid of zigzag algebras all glued in infinite directions together, and you have some squares compute relations. So it's really infinitely more complicated in the good sense than the good old quantum group itself, as it should be, right? The binomial just vanishes of arbitrary high order. So this is a very nice fractal quiver. Okay, I can stop here, or I just continue for the next 4 minutes to show you work in progress, because I really claim up to my original sin, this completely generalizes. So here you have some nice zigzag algebras glued according to their digits into one another, and something similar will happen in characters for SL3 or whatever. So let's do SL3. Let's just try to do it. So sorry. Same strategy. I would do the same strategy. I would have to make sure that there are no poles, so exactly the same problem, but I would do exactly the same strategy and almost nothing changes. Okay, my web category looks a bit more complicated. You have seen those web categories for SLN actually, or for GLN in Lulu's talk and in Manuel's talk, but it's kind of the same idea. You take the fusion rules, you have one direction for everything, you can write down, now it's really due to Ben, you can write down an integral basis according to the fusion rules. You can write down a standard basis, but just, oh, I forgot to put projectors here, but just putting the projectors everywhere, so there should be projectors, and here should be projectors as well. You can define a tilting basis, and you stick them all together to get exactly the same pattern, and then you want to compute the base change. Here's an example. So standard basis, no projectors. Tilting basis, you stick in projectors. Standard basis, you stick in projectors. Artin-Wedderburn basis, tilting basis, you stick in tilting projectors, and you want to compute the base change matrix between the two, and you get a quiver for SL3. And just to give you a hint, so this is usually how those, like you take paths in the positive wild cone, they will look like this. For instance, here's 3 paths, here zillions of paths, and the red paths are not allowed because they leave the positive wild cone. And you take all those paths and you build all those projectors. And you compute those base change matrices, and you're done. And so this is basically how the tilting characters look like for SL3, right? They have this nice folding pattern. So the tilting module, which sits here for SL3, somewhere has all those Weil factors in its expression. So you would take the corresponding projectors and just sum them all up, and you get a well-defined projector projecting to the tilting. Okay, and I think I'm basically out of time. Thank you very much.
Daniel, are there questions? So if you know the tilting characters, you basically get for free that this linear combination is going to have no poles.
Yes, it's basically an argument that you go to something like QP, and in QP you only have to make sure that you end up in ZP, which you can specialize to characteristic 0 or to characteristic P. It's an idempotent lifting argument. That's
yes, I agree.
Hi, Daniel. Great talk.
Hi.
I have a question.
Who is talking? Sorry.
Elijah.
Ah,
I guess I have a couple questions. Maybe the first one I'll ask is, you said that this should work for like classical types, but why wouldn't
yes. As
your
soon as
approach?
I'm in webs, I think I can just copy Ben's strategy of, I mean, Littleman pass and this whole strategy should work for all types. I
Yes,
just don't know the web calculus.
certainly. But I guess why wouldn't it work in like F4 or whatever?
I wouldn't call F4 classical type.
Oh, okay.
The problem is the way I want to think about tilting modules is they are direct sums of tensor products of a vector representation. I don't know what the vector representation for F4 is supposed to be. Right? You would, in principle, it would work for F4 as well. I just
Sure.
don't want to think about F4.
The other question that I had was about the scalars that you said are in your SL2 quiver.
Mm-hmm.
If you studied those scalars more closely, would you be able to understand the mixed characteristic case?
Yes, I think so. I think the mixed characteristic is just a matter of bookkeeping. It will get, it should be a little bit easier. It should be infinity minus one, but it will get kind of tricky to write it down because you have quantum numbers and you have usual numbers. So I just don't, I think it should be doable. I think it's interesting to do it, but yeah, we never did it.
I see. So, but the scalars aren't in, so the scalars are not written.
All those scalars are written explicitly in our paper. So yeah.
The application just hasn't been done.
They're actually very nice functions that turn up in number theory, like whatever, I forgot, but they're not too complicated.
Okay. And then my last question, sorry, I mean, nobody ever asks questions at these things, so I'll just ask another one. You express the P. Jones-Wenzels in terms of the characteristic zero Jones-Wenzels, like here. If I, instead of the characteristic zero Jones-Wenzels, I used the quantum group Jones-Wenzels at a p-th root of unity.
Yes.
That
should also work.
That should also work, but are the formulas become somewhat nicer in some cases? Like it would just be one thing equals the other thing. I guess what I'm asking is there a way to maybe make this manifestly positive by using Q Jones? No.
So the only thing I never tried to express a P. Jones-Wenzel in terms of the quantum group Jones-Wenzels, but the only thing I can guarantee that it will cut the expression in half, right? Because now I'm using characters, so generation whatever, and they express it in terms of generation zero, and they would just go one generation higher, but I don't know anything about transitivity. I never tried.
So, I mean, I have maybe a slightly more general question, which is like,
Go ahead.
I mean, this approach of understanding, these tilting modules by looking at these tensor powers. I mean, it's a very well established approach. Like, there's the whole theory of Schur algebras. So, like, somehow, what are you going to learn that people weren't able to figure out by thinking about Schur algebras for a few decades, right?
Oh, that's a good question.
They know cellular bases for the Schur algebras. So, like,
well, I'm not saying that the bases I wrote down are new, right? I mean, they're basically Ben.
It's a different basis than the Schur algebras.
Mm-hmm.
It's a basis that's adapted to the monoidal structure, which the Schur algebra one isn't.
Mm-hmm.
Oh yeah, for example. Oh yeah, I haven't talked about the monoidal structure at all. Okay, so that's another open question to give not just a presentation as a category, but as a monoidal category. So decomposed tensor products of those funny projectors.
Okay.
It's a very different thing than the Schur algebra.
All right.
It's just like a very different I mean, you know, when you have a cellular algebra, you get a million other cellular algebras by any upper triangular change of basis.
I showed you 3 actually, yes.
Yeah, exactly. But then they're not all guaranteed to be the same integrally in some sense. Like they can give you different integral forms of the category.
Mm-hmm. Sure. Well, right. I mean, again, as illustrated in the talk. Yeah, I mean, similar like this BCD case, right? You have these, what do they usually call them? Like affine Brouwer type things.
Do we have more questions? That was a very nice talk. Thanks, Daniel.
My pleasure.